Today we're going to be talking about reaction mechanisms and rate law, and we are going to be reviewing and combining some of the topics we've talked about in previous videos. We've talked about the fact that many reactions take place in more than one step, that these individual steps are called elementary reactions, and that the sequence of steps by which a reaction occurs is called the reaction mechanism. Now, when we have a reaction mechanism in which each elementary step is irreversible, that means the reaction proceeds in one direction like this and is not in equilibrium like this. So, if each elementary step is irreversible, or if the first step is rate limiting, the rate law of the reaction will be set by the molecularity of the slowest elementary step. In other words, the rate-limiting step. Hence, we should be able to determine the rate law for these types of reactions based on the stoichiometry of the equation. And this is the sort of thing we did in a past video. But if we look at this more closely, we can see a pattern. The rate law is not only determined by the stoichiometry, it's determined by the molecularity, which is basically the number of molecules or ions that are participating in the rate-determining step. In a unimolecular reaction, there is only one species reacting. Maybe it's just changing into another type of molecule, maybe it is decomposing into more than one molecule, but there's only one reactant. Such a reaction might be represented by an equation like this, where A goes to some sort of products. Our rate law for such a reaction is rate equals K times the concentration of A. Notice that this is a first-order rate law. In fact, all unimolecular reactions have first-order rate laws. In bimolecular reactions, you have two ions or molecules or species that are reacting to form products. Sometimes you have two different species colliding, and sometimes you have two molecules of the same species. And when you have two different species reacting, you get a rate equation like the one on the top, and when you have two molecules of the same species reacting, you get a rate equation like the one on the bottom. Both of these bimolecular reactions are second order. Bimolecular reactions always have second order rate laws. In a termolecular reaction, three molecules or ions collide at the same time. There are several ways this can happen. Perhaps three of the same species collide with each other. For this, you get a rate law, rate equals K times the concentration of A to the third. Perhaps you have two molecules of one species and one of the other that collide at the same time. And in this situation, you would get this rate law. Or perhaps you have three different species colliding at the same time, and you would get this rate law. Notice that all three of these rate laws are third order. Termolecular reactions always have third-order rate laws. This table summarizes the relationship between molecularity and rate law for unimolecular, bimolecular, and termolecular reactions. Let's summarize. For reaction mechanisms in which each elementary step is irreversible, or in which the first step is rate limiting, the rate law of the reaction is set by the molecularity of the slowest elementary step. In other words, the rate limiting step.